World War II aviation was often judged by speed, altitude, and raw firepower. Aircraft were compared on paper, and the fastest designs were expected to dominate the battlefield. But real combat exposed a different reality. Aircraft failed under stress. Structures broke. Pilots were lost, not because they were outmatched, but because their machines could not survive sustained combat conditions. Naval aviation, in particular, demanded aircraft that could take damage, return to carriers, and operate reliably day after day. Edward H. Heinemann approached this problem differently. He did not design aircraft to win performance charts. He designed them to survive combat, deliver their payload, and come back. By controlling weight, simplifying structure, and eliminating unnecessary complexity, Heinemann created aircraft that worked when theory failed. His most famous design, the SBD Dauntless, would prove this during the Battle of Midway, where reliability and structural integrity mattered more than speed. This video examines how Edward Heinemann's engineering philosophy reshaped American naval aviation during World War II, and why an aircraft designed for survivability and precision could change the outcome of a battle long before pilots ever saw the enemy. Edward Henry Heinemann was born on March 14, 1908, in Saginaw, Michigan, United States. He grew up during a period when aviation was transitioning from experimentation to industrial production. Unlike many later aerospace engineers, Heinemann did not come from an academic or scientific elite. His early environment did not revolve around theoretical research or advanced mathematics. Instead, it reflected the practical, industrial culture of early 20th century America. Heinemann showed an early interest in mechanical systems and aircraft structures. His education followed a technical and engineering-oriented path rather than a purely academic one. He studied aeronautical engineering, focusing on aircraft construction, structural strength, and weight management. From the beginning, his attention was directed toward how aircraft behaved under real operating conditions rather than idealized assumptions. In the early 1930s, Heinemann joined Douglas Aircraft Company, one of the most important American aircraft manufacturers of the era. At Douglas, engineering decisions were closely tied to production constraints, maintenance realities, and operational feedback from pilots and naval planners. This environment reinforced Heinemann's belief that aircraft design was not about maximizing specifications, but about balancing performance, durability, and manufacturability. Heinemann quickly distinguished himself as an engineer who paid close attention to weight control. He treated weight as a critical enemy of aircraft performance and survivability. Every additional component was examined for necessity. If a part did not contribute directly to mission success or structural integrity, it was reconsidered or removed. This approach was not about cost-cutting, it was about improving range, payload capacity, and damage tolerance. By the late 1930s, as global tensions increased, the US Navy required carrier-based aircraft capable of operating in harsh maritime conditions. Naval aviation imposed unique demands: short takeoff distances, arrested landings, exposure to salt water, and the need to survive enemy fire while returning to carriers. Heinemann became deeply involved in addressing these constraints through structural simplification and robustness. His most important pre-war and early wartime contribution was the design leadership behind the SBD Dauntless dive bomber. On paper, the SBD was not exceptional in terms of speed or advanced technology. It lacked the raw performance figures of some contemporary designs. However, Heinemann engineered the aircraft to be structurally strong, aerodynamically stable during dives, and capable of absorbing damage. Heinemann paid particular attention to load paths, reinforcement of critical structural elements, and the elimination of unnecessary complexity. The Dauntless was designed to withstand the extreme stresses of dive bombing, a role that imposed severe aerodynamic and structural loads. This focus on structural integrity allowed pilots to execute steep dives accurately without losing control or destroying the aircraft. Equally important was reliability. Carrier operations allowed little margin for mechanical failure. Aircraft had to start, launch, fight, and recover repeatedly under combat conditions. Heinemann's design philosophy emphasized systems that could be maintained easily and repaired quickly. This ensured high operational availability during sustained operations. When the United States entered World War II, the SBD Dauntless was already in service. Its true value became clear in combat, particularly during the Battle of Midway in 1942. In that engagement, the Dauntless proved capable of delivering decisive strikes against Japanese carriers while surviving intense anti-aircraft fire. Many aircraft returned heavily damaged but intact, a direct result of Heinemann's emphasis on strength and survivability. By this stage, Heinemann was recognized not as a theorist, but as an engineer whose designs performed under the harshest conditions. His approach demonstrated that aviation success in war depended not only on speed or innovation, but on disciplined engineering choices grounded in operational reality. This philosophy would continue to define his work throughout and beyond World War II. The true test of Edward Heinemann's engineering philosophy did not occur in design offices or wind tunnels. It occurred in combat. When the United States entered World War II, the SBD Dauntless was deployed as the primary carrier-based dive bomber of the US Navy. Its role placed it directly into the most dangerous operational environment of the war, attacking heavily defended enemy ships from high altitude under concentrated anti-aircraft fire. Dive bombing imposed extreme demands on aircraft structure. The Dauntless was required to enter steep dives at high speed, maintain stability during descent, release its payload with precision, and recover safely without structural failure. These maneuvers generated high aerodynamic loads and stress concentrations that exposed weaknesses in poorly designed airframes. Heinemann's design choices directly addressed these conditions. The SBD's structure emphasized strength where it mattered most. Critical load-bearing components were reinforced to handle repeated high-stress dives. Control surfaces were designed to remain responsive under high dynamic pressure. The aircraft's perforated dive brakes reduced speed during descent, limiting aerodynamic stress while improving bombing accuracy. These were not cosmetic features. They were structural solutions to a specific combat problem. Equally important was survivability. Heinemann understood that aircraft operating over enemy fleets would be exposed to sustained anti-aircraft fire. The Dauntless was designed to absorb damage without catastrophic failure. Structural redundancy allowed the aircraft to remain controllable even when hit. Fuel and control systems were arranged to minimize the risk of immediate loss after damage. This did not make the aircraft invulnerable, but it significantly increased the likelihood of return. Carrier operations amplified these requirements. Aircraft had to withstand repeated arrested landings, rough deck handling, and exposure to corrosive maritime conditions. The Dauntless was engineered to tolerate these stresses while maintaining reliability. Mechanical simplicity and accessible systems allowed ground crews to perform rapid repairs between sorties. High sortie rates were critical during sustained naval engagements. These design priorities became decisive during the Battle of Midway in June 1942. American dive bombers faced strong fighter opposition and intense shipboard anti-aircraft fire. On paper, the Dauntless was slower than many Japanese fighters. In practice, its stability in the dive and precision in bomb delivery allowed US pilots to strike vulnerable points on Japanese carriers with devastating effect. The success at Midway was not the result of superior speed or advanced technology. It was the result of an aircraft designed to perform its mission reliably under combat stress. Many Dauntless aircraft returned to their carriers heavily damaged. Wings were perforated, control surfaces were hit, and, Engines showed signs of battle damage, yet the aircraft remained structurally intact and controllable long enough to recover. This outcome directly reflected Heinemann's emphasis on structural integrity and damage tolerance. Operational feedback from Midway and subsequent battles reinforced Heinemann's engineering principles. Naval commanders valued aircraft that could be depended on to deliver results, rather than those that promised theoretical advantages. Reliability, maintainability, and survivability proved more important than marginal gains in speed or climb rate. The Dauntless continued to serve throughout the war, participating in major Pacific engagements beyond Midway. Its effectiveness declined only as newer aircraft with similar design philosophies, but improved performance became available. Even then, the SBD's reputation as a dependable combat aircraft endured. Through the Dauntless, Edward Heinemann demonstrated that aviation engineering success in World War II depended on disciplined trade-offs. By prioritizing weight control, structural strength, and operational reliability, he produced an aircraft that performed consistently under fire. This approach did not generate headlines during development, but it produced decisive results when combat conditions exposed the limits of theory. Edward Heinemann's influence did not end with the success of the SBD Dauntless. World War II validated his engineering philosophy, and that philosophy continued to shape American aviation in the years that followed. The lessons learned from carrier combat reinforced a simple conclusion: aircraft design had to be driven by operational reality, not theoretical performance targets. After the war, the US military faced a rapid transition. Aircraft speeds increased, missions diversified, and new technologies emerged. Despite these changes, the core constraints Heinemann had worked under, weight, structural integrity, maintainability, and survivability, remained unchanged. Heinemann continued to apply the same disciplined approach to new design challenges at Douglas Aircraft. One of the clearest demonstrations of this continuity was Heinemann's later work on jet aircraft. As propulsion shifted from piston engines to jets, many designers focused on speed and altitude as primary measures of success. Heinemann resisted this tendency. He continued to treat weight as the central variable that governed performance, range, and survivability. Excess complexity was still viewed as a liability. This mindset culminated in the development of the A4 Skyhawk, an aircraft designed well after World War II, but directly shaped by Heinemann's wartime experience. The Skyhawk was compact, lightweight, and structurally efficient. It required no folding wings, no complex mechanisms, and minimal maintenance. Although it belongs to a later era, its design philosophy can be traced directly to the lessons learned from the Dauntless. The Skyhawk demonstrated that Heinemann's approach was not limited to a single aircraft or conflict. It showed that disciplined engineering choices could outperform larger and more complex designs, even as technology advanced. This reinforced the idea that effective aircraft design depended less on novelty and more on understanding mission requirements precisely. Within the broader American aerospace industry, Heinemann's methods influenced how engineers evaluated trade-offs. His work emphasized that every design decision carries cost in weight, reliability, and maintainability. These trade-offs became central considerations in post-war naval aviation planning. Aircraft were increasingly judged on how well they supported sustained operations rather than isolated performance metrics. Heinemann was known within engineering circles as a demanding but practical leader. He expected rigorous justification for every design feature. Components that did not directly support mission success were challenged. This culture of accountability shaped engineering teams and reduced unnecessary complexity. The result was aircraft that were easier to operate, easier to maintain, and more predictable in combat conditions. Importantly, Heinemann's legacy was not based on experimentation for its own sake. He did not pursue radical configurations without clear operational benefit. His designs reflected a conservative but effective engineering mindset, focused on reliability under stress. This approach proved especially valuable in naval aviation, where failure rates had immediate consequences. By the end of his career, Heinemann had established a clear model for how military aircraft should be designed. His work showed that success in aviation warfare depended on aligning engineering decisions with the realities of combat operations. Speed, power, and innovation mattered, but only when they supported survivability, precision, and reliability. Edward Heinemann's contribution to World War II aviation was therefore not limited to a single battle or aircraft. It lay in demonstrating how disciplined engineering could translate directly into combat effectiveness. His designs did not promise perfection. They delivered performance where it mattered most, under fire, over hostile territory, and in the demanding environment of carrier warfare.